Welcome. It's good to see you. You guys had a good weekend. Nice sleeping in, all that good stuff. We're going to do two things today that are related to one another. We're going to handle any homework questions that you have. And I also want to take a look at gears, in particular number 73, so that we can learn a little bit about how gears function and how simple machines work. So, if you have any homework questions, now is a great time. Yes, sir.
The last one, number A. Letter A.
The last one, what number was that?
33? 37? 37.
37.
We looked at B.
There aren't any A's or B's on 37.
Okay, well, the first part, yeah.
Which number are we talking about?
37.
37.
I'm able to find it in the time, but not the, how many revolutions were made.
Okay, so we have a centrifuge rotating at 10,300 RPM, which I'm going to write as revolutions per minute. And how do I label that information? What is that?
Angular velocity.
Yeah, that's right. That's going to be an angular velocity, and it's the angular velocity at the start of the problem. So we're going to call that omega 0. And we're also told that this thing comes down to rest. So immediately I write omega equals 0. And we're told that it's brought to rest by a frictional torque of 1.2 Newton meters. And we're told that the mass of this cylinder is 4.80 kilograms, and that it is basically a solid cylinder with a radius of 0.0710 meters. And now they ask some questions. A question: through how many revolutions will the motor turn before coming to rest, and how long will it take? We have to answer these two questions. We can see that this is definitely a multi-step problem where we're going to have to figure something out and figure something out based on time. Yes?
I can't divide my answer by 10,300, right? That wouldn't work.
You could randomly divide it by 10,300, but what would it mean?
My answer is 10.9 seconds, is what I got, which I look up as the answer. Could I do that and get that how many revolutions it would be?
No, because the speed's changing.
That's why I figured it.
Yeah, the speed's changing, right? All right, so tell us what you did with this.
First I did torque equals inertia times alpha.
Good.
And then with the inertia, it's the from the chart, it's the 1/2 mr squared.
Yep, that's right.
And alpha is change in W.
Snacking.
Sorry.
You said W.
Omega times change in, or over change in time. So then you have everything except the change in time.
Good.
And I set everything, I did all the algebra for it, and set everything equal to change in time. That's how I got the change in time.
Okay. This is great, Blake. You did everything that was hard. Meters, and that's squared times change in omega over change in time. And when you computed the change in time, you got 10.8 seconds, 10.9?
It was like 10.87.
All right, so 10.9 seconds, yeah. Excellent. Yep. Now, there's just a small thing we got to figure out about the signs, because technically the change in omega is negative, right? Because we're going from a high rate of speed to a low rate of speed, so the change in omega is negative. So we wonder, does that mean the delta t is -2? That seems strange. That's not quite right. Where does my corresponding negative sign show up?
Torque.
Yeah, the torque is negative. Right there. Yep. Because it's opposing the direction of motion. Good. Very good. Okay. So now they ask another question, which is how many revolutions is it going to turn through? And so how would we label what we're looking for? It's light distance, but it's in a rotational sense. So it would be...
Would it be the kinematic for this?
Yeah, exactly.
So
What?
Delta theta.
Delta theta, that's right. It's the quantity delta theta, which is the angular displacement. And so now this encourages us to think about the equations of motion that we have. A couple of ways we can go about it. No, that's omega, if you're thinking that. Because the alpha is the rate of change of omega. What is it? Delta theta equals.
Omega
W?
0t minus 1/2 alpha theta, or
Plus 1/2 alpha t squared. And smack him again for the...
he already did, don't
All right,
worry.
good. Oh, all right, good. And so now, Blake, what do we have here? Well-
The initial of omega
Mhm.
is 10,300. Time is 10.9. The angular is for alpha is dw over 10.9. Oh, omega. I'm sorry. Go ahead.
Apparently, the meetings will continue until compliance is assured. Okay. And what do you have for your alpha here? Don't write this down yet, guys.
Alpha would be somewhere to south of 10.9 divided by.
Yeah. Well, it's the delta omega over delta t, right?
Yeah.
So you're going to have
Whatever that is.
whatever that is.
That should do it right
don't
now.
you have to convert to
Yeah.
seconds?
While he's computing that, I want you to picture what's going on. What we have is this thing that's rotating really, really fast, right? And we turn off the power switch, and now it experiences a frictional force, and that frictional force is going to start to slow it down. And so as it slows down, this thing keeps on turning, until it finally comes to rest. And we're just asking, how many times did it turn for? What do you get?
945.
945. 45, okay? And so then you plug all this in and you get a huge answer. This is going to be 100,000 plus 945 is going to be somewhere in the hundreds of thousands, all right? And then you go to look up your answer, and tragically the answer is like somewhere around 600 or 900.
Well, is it in radians?
Ah, well, it's 900 revolutions-ish, yeah?
How'd you find delta T?
He found the delta t because he plugged in here, and he knew the initial and final omegas. He thought they were w's, but he knew what they were. Okay? And so he simply plugged them in and solved for delta t. I would clear the fractions by multiplying both sides by delta t, and then you can just divide. As far as the algebra goes. So you have the insight that your problem might be what?
Wrong.
No, your problem might be what?
What did you do wrong?
Yeah.
No.
Oh no! What's the insight we need? What's possibly his problem here? Units. Exactly. Let your units be your guide. Of course, you can't do that if you don't put the units in there. Because we deal with seconds and minutes and years and so on and so forth, you have to watch out for your units. Because we deal with radians, revolutions, degrees, you have to watch out for your units. And that didn't happen. All we had here were numbers.
All right, well, 10,300 minutes.
No, it's not.
Well, I mean, sorry, revolutions per minute. Seconds, which is 10.9.
Uh-huh. And see, there's your problem.
And then it would have to be divided by.
Oh, that's in seconds.
Yeah, that's in seconds. So we need some minutes
So you
going
divide that
on.
by 60.
Yep. So how many minutes are we actually talking about here?
About
5.5 minutes? 10 seconds is 5.5 minutes?
No, I did wrong. 0.18.
0.18 minutes. That sounds about right. Okay. Plus. Now we have our alpha. What is the alpha that you got?
Great. 945.
What's the
945, no. Omega. No,
omegas aren't units?
for,
Uh-oh. Let's go back to how you computed it. What's happening here is that you have acquired a bad habit. Students will do this, and that is the bad habit of not putting your units in with every single thing. Now, you've heard me say this like a bazillion times, and you probably said, that's teacher going wah, 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 like Charlie Brown, right? Wah, 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 wah. And then we actually hit a situation where the only mistake that you make is your units, and you go, oh, now I get it. I'm supposed to put the units in so I don't make these kinds of mistakes. So let's go back to where you computed the alpha. You told me that alpha was equal to delta omega over delta t. You didn't say omega that time. And now tell me what quantities you put in there for that.
seconds and,
No, tell me what quantities you put in there.
sorry, 10,300 and 10.9.
10,300 was your final.
No, okay, 10,300.
Let's think it through carefully.
Per minute.
Delta omega is final minus initial. Give me final and initial.
Alright, initial is 10,300 revolutions per minute.
Yeah.
Final is 0 revolutions per minute.
So it should go how? What minus what?
10,300 revolutions per minute. Minus, no, sorry, other way around.
Yes. Notice that we had to slow down and think about which one was final and which one was initial, right?
My bad.
And that's going to matter because when we come back up here, we're actually going to put in a negative value, and that's going to decrease the total number of revolutions that we have. If we had a positive alpha, that would mean that we're actually speeding up, and we would have to increase. That would result in an increase. All right, and then you had 10.9 seconds here.
And then negative 945 revolutions per minute per second.
Yeah, that seems awkward, doesn't it?
And then you do divide it by 60.
How about, instead of the 10.9 seconds, let's use the 0.18 minutes that you gave me before. And now we have less awkward units. We'll need a new number, though.
Got it. But 57,000, or negative 57,222 point.
That's good.
222.
That's good. And that's revolutions per minute squared. Per minute per month. And now finally, for our time, we have 0.18 squared. And now I think this computation will give you much greater happiness. Somebody punch it in for him. He's done a lot of hard work. Tell us what we get.
Got 334.
I get 927.
So wrong.
This is wrong?
It's supposed to be 993.
993. There may be some rounding issues here. We have 0.18 and 0.18. So it may be that we ended up rounding funkily. With 0.18 as our time, this is actually the correct answer here. Now,
It just seems like it's off by a lot.
It does seem like it's off by a lot, and I don't know if that means that they dorked up. Do we have the right, time?
Yes.
.182. If I use .182, then I get 940, 937.
Still off by.
Yeah, I think we're right, actually. Given their time here, then this is correct. 937 is slightly more. Okay, so what's learned here is that putting your units in is a part of being skillful craftsman. And so you're just going to do it. I know it's annoying, but eventually it becomes not annoying because eventually it saves you from enough mistakes that you see value of it. All right, I'd like to talk now about gears. We have a little bit of time. Please turn to number 73. And at number 73, what we have is a bicycle. And there it is. And maybe how many of you have a 10-speed bike or a bike with a certain number of speeds? 10-speed used to be the thing, now it's 24, 18, or whatever. All right. And so here's how it works. We're going to have two gears, and they're going to be connected by a chain. Actually, these are called sprockets rather than gears, but gears function exactly the same way, except that they push off each other with teeth. So I'll use the right term. We're going to have two sprockets that are going to be connected by chain, and the sprockets are going to have two different radii, R and R. This is going to be where we pedal on a bicycle, and this is going to be where the back wheel is on a bicycle like that. And the front wheel is unpowered. I don't think I've ever seen a front wheel powered bike. Really?
Yeah, for like the X Games where they have to go over like rocks and logs and stuff, they have two-wheeled powered bikes.
Really? And some weird differential kind of a thing going on? Wow, cool. Okay. All right.
It's for like
Now, here's what happens. We're going to rely on two things that don't change. The first thing that does not change is the length of the chain. The chain length is exactly the same, and because as it goes around. And because of that, that means that the speed of the chain here and the speed of the chain here, and I'm talking about the linear speed of the chain, the amount of chain that goes past the sprocket, has to be the same for both sprockets, because the length of the chain doesn't change. So whatever I pull here has to get fed through over here. Everybody see that? So the velocity is the same. And we know, so let's call this V1 and V2, but V1 equals V2. How about V big R, V little r? That's better. So this is our first invariant. Now let's see where this carries us. We know that if an object is moving along the edge of the circle, that its speed is given by radius times angular speed. So if we set these two equal to each other and solve, we find that these angular speeds are proportional to each other. But notice that they are inversely proportional to each other. If the angular speed is the speed of the wheel, and the angular speed here is the speed of the pedals, then I can see that if this is a fixed radius right here, and I can change this by changing gears, then the smaller the gear, the larger the speed of the wheel. And this is exactly what you've experienced if you've ever ridden a 10-speed bike. If you click it into 10th gear, you're going to go really fast. You have a little tiny gear there on the back. So the first thing we see is the relationship between the gears, and we call this the gear ratio, or the sprocket. It's called a gear ratio even if it's sprockets. I know, it sounds like a jet airplane. Are they sure that was a false code ring? And you can see that the larger that the pedal gear is compared to this one, then the faster you're going to go. Yes?
So since the linear speed doesn't change, then what's the point of switching gears?
That's a great question. Because this is the wheel speed, this is the pedal speed. So if I use, let's say I have a gear ratio that's 5 to 1, which is really excessive. Okay? So this is 5 times as big as that. To do that, I have to have this big old massive thing all the time. Then this would mean that the wheel goes 5 times as fast as I pedal. So I pedal once, and my wheel back here goes around 5 times.
In the rear gear.
Yes, exactly. So I'm going to be able to haul out.
But it's a small gear, so like it wouldn't go. I mean, the linear speed doesn't change anyways. And
Correct. But the trick is that it's the linear speed around the gear, not around the wheel. And it's the wheel that's actually driving the bicycle.
oh,
You see it? Yep. Good, good, good. Great question. The chain drives the gear, but the wheel drives the bicycle. So so the angular speed of this is what matters, and not the linear speed of the gear. Okay, now, let's do one other thing though. I said there are 2 invariants. Here's the second one. Do you believe in Newton's third law?
I guess.
Yes.
I believe in Newton's third law. For every action there's an equal and opposite reaction. That means that the force that is exerted by the pedal, well, I guess I got to do it here, right? Because the pedal's taking it around this way. That was kind of exciting. Has got to be equal but opposite to the force that drags my feet as I try to pedal. Okay? So the force at little r has to equal the force at big R, just like that. Now, how can we define that force? Well, we're going to define it in terms of torque. And we're going to say that the amount of torque, remember that torque equals force times radius, right? So we're going to say that the amount of torque at big R divided by the radius at big R equals the torque at little r divided by the radius at little r, because the forces have to be equal. And now if I do a little bit of cross multiplying to solve, I can see that once again there is a proportion, and the proportion is between the torques and that gear ratio, right there again. The gear ratio determines the ratio of torques. So that the larger my gear ratio is, the more torque has to be exerted at the drive sprocket in order to get the wheel over here to rotate. So if I again do a 5 to 1, this means that I'm going to have to exert 5 times as much torque here in order to get this guy to go right here. In other words, if I'm in 10th gear, I'm going to go really fast, but I have to exert a lot of torque to make it happen. If, on the other hand, I'm in 1st gear, then now I have a larger radius for little r, my gear ratio is smaller, I don't go as fast, but I don't have to exert as much torque either. What would that be suitable for? What kind of terrain? Going up hills, that's exactly right. So if I'm going up hills, I'm going to put it in a low gear. I have to spin like crazy to make progress, but I can actually do it. If I'm going downhill, I'm going to put it in 10th gear, where gravity can assist me on providing that torque, and I can go like a, literally. Yes?
so I still don't get why the big R's will be a small R. I mean, I understand the Newton's third law, but don't like these two forces pointing at the same direction?
No, remember? Oh, I see. Yes. Yeah, you're right. And I probably should have drawn it like this. It's a resistive force.
But why though?
Honestly, this is the best way to do it, like so. My foot is being resisted, and the wheel here is being driven. That's the best way to see it.
So the foot works on the like front here.
Yes, the foot turns this way. Because the foot turns this way, the chain pulls back on it in this way. So the resistive force that the foot feels is going to be equal but opposite to the force that...
So that force is what exerting the force on what?
This is the force being exerted on the chain as it goes this way.
Alright,
That's driving the bike wheel.
okay.
Okay? And it in turn is equal but opposite to the force that the wheel is experiencing from the pavement, right? Yep.
So that friction goes that way, and then we just.
Yeah, exactly. Now, we've got some people with some experience with gears and driving. That would be these two here. Tell us about how gear ratios work on your robot.
We have a drivetrain that has a 1 gear ratio, I guess.
Why would you want a 1-to-1 gear ratio? What's the point of that?
You don't want to direct that. You don't want to direct
Gotcha. So there's things other than simply gear ratio that matter here. You don't want to directly put stress on your motors if you can possibly help them. All right? And you have another gear setup?
Yeah, we have some
Okay. How about you guys?
I was not participating, I did not participate in that.
Okay. I happen to know a little bit about it. They have a gear ratio that is actually it's actually 2-to-1. So their driving here is twice as big as that one there, which means that they exert less torque, but they can go like crazy. They go really, really fast if they need to. They originally had 3-to-1 and decided it was a little bit excessive. The downside of what you guys have is that if the ramp were much steeper, you'd have a hard time getting up. Last year, there was a need to lift a fairly heavy arm, so they actually used a 27-to-1 gear ratio, where the drive wheel was 1 and the load was 27. And the result was that they were able to slowly move a heavy arm all the way over like so. Again, with the power of gears approach. So there it is. So these kinds of things have practical uses. The same approach happens in your car. When you get into 5th gear, then your car is using the car changes the size here, right? And it uses a relatively small gear here compared to the gear from the drive box there. And as a result, you can go at high speeds, like 65 miles an hour, in a small number of reps. The other day, I got on the highway in my wife's minivan, and I'm not totally used to it. And I'm driving along, and my ear is telling me that my engine is revving too fast. And I looked at the tachometer, and sure enough, my engine was going at 5,000 RPMs. It usually hits around 3, right? 3 is kind of normal. So I thought, why is this? And I looked, and I'm like, I'm going 65 miles an hour, and I'm in 2 instead of drive. So I had to quickly shift, and there it was. It didn't do any damage. It wasn't in the red zone or anything like that. But your ear tells you really how fast the RPMs are going, and if you want your engine to have to go slower, then you put it into a higher gear. That's it. Okay. I have no idea how many minutes we have. Maybe 3? 2? Are there any questions?
Second.
That you might say?
Second.
Everybody.